Welcome back, students. In this video, we're going to look at reduction reactions where we reduce to alcohols. First, let's look at the idea of reduction and oxidation within the context of organic chemistry. Your textbook likely has a section on this where they talk about oxidation numbers, but I want to go more general than that. I want to go ahead and define the reduction as either adding hydrogen or removing oxygen, whereas oxidation is adding oxygen or removing hydrogen. When I consider the cycle over on the right-hand side, what I notice is here I have one bond to oxygen, and over here I have two bonds to oxygen. So in a way, I'm adding oxygen. So going from an alcohol to a ketone would be oxidation. Notice how I also lost a hydrogen during that process. Whereas if I'm going the other direction, a ketone to an alcohol would be an example of reduction, because I'm losing a bond to oxygen and I'm adding a hydrogen during that process. So we're going to keep that as our definitions for reduction and oxidation as we move forward. Let's talk about the reduction of aldehydes, which forms primary alcohols. There are three reagents that you're going to see commonly used: hydrogen with either platinum, palladium, or nickel catalyst, sodium borohydride with methanol, MEOH, as a solvent, and then a two-step reaction where you use lithium aluminum hydride and a second step of water or H3O+. Lithium aluminum hydride has a structure that looks like this, where the aluminum is negative and there's a positive lithium counter-ion hanging out next door. Lithium aluminum hydride is sometimes abbreviated as LAH. It can also be abbreviated as LiAlH4, which is the chemical formula. Now that we have that down, let's see that all of these reagents will take the aldehyde to a primary alcohol. So all of these will give you the same product at the end. They all give you the primary alcohol. What if we started with a ketone? Well, if we start with a ketone, all of these reagents, notice they're the same as what we saw on the prior page, are going to get you to a secondary alcohol. So you get the same product for each of them. You start with a ketone, you get a secondary alcohol. Lithium aluminum hydride is special, though, because it is the strongest of these three reducing agents that we saw on the prior page. So strong that it can react with things that hydrogen and sodium borohydride, the NaBH4, cannot. So lithium aluminum hydride can react with carboxylic acids and also esters. So when lithium aluminum hydride reacts with a carboxylic acid, what you end up getting is this. And when it reacts with this ester, you're actually going to get the same product. Next, let's consider the mechanism of lithium aluminum hydride. Here I'm going to have lithium aluminum hydride react with a ketone. Notice lithium aluminum hydride and sodium borohydride, if you look up the mechanism for sodium borohydride, it's remarkably similar to the one for lithium aluminum hydride. So I'm only going to show you the lithium aluminum hydride mechanism. What happens is, in both of these cases, is that the hydride, which is a hydrogen plus its electrons, attacks the carbon of the C double bond O. So your pair of electrons and the hydrogen attack here. That opens up this pi bond. It breaks it, and those electrons go on to the oxygen. Now I have an oxygen that's negative, and I just added a hydrogen. At this point, we've made something that's called the tetrahedral intermediate. That tetrahedral intermediate can't do a whole lot. All that we can do at this point is protonate it. So what you'll find is that there'll be protonation in a second step. Some textbooks will utilize water as their proton source and some will use acid. I think in real life, the safest thing to do would be to start with water because lithium aluminum hydride is super scary reactive. So I would react or allow water to react first until all the lithium aluminum hydride had reacted. And then I would add a little bit of acid and then finally check the pH to make sure it's neutral. And that's way I would know that I'm finished with my reaction. So don't be surprised if you see some people write water here and other people write acid. So what will happen is your oxygen will pull off this proton and you'll get a proton transfer so that you end up with your secondary alcohol. Now, in this instance, when we got to that tetrahedral intermediate, we were essentially done with the reaction, right? All we needed was to add water in a separate second step for that proton transfer. But if we were to change this, let's pretend that instead of starting with a ketone, we started with an ester. And I'm going to write OET here. That ET stands for ethyl, right? So this is an ester where we have oxygen and then an ethyl group attached to that oxygen. If we allow this to react with lithium aluminum hydride, the process is similar, but a little teensy bit different. The starting point is the same. You still have this end up happening. And when you form the tetrahedral intermediate, now what you need to do is ask yourself a question. Do I have something that can leave? And the answer is yes, your OET in this case is going to be a good leaving group. Now you might be thinking, well, in substitution reactions it wasn't. Yeah, but this isn't a substitution reaction. So what can happen when you do have a good leaving group is your pi bond can reform by the oxygen having an extra pair of electrons, that electron pair collapsing, reforming the pi bond and kicking out the OET. Now what has happened is we form an aldehyde. Well, guess what? Aldehydes are reactive with lithium aluminum hydride. So lithium aluminum hydride will attack again. Now I'm going to draw my second molecule of lithium aluminum hydride, and it will go ahead and attack the carbon of the C double bond O. That C double bond O is called a carbonyl group, by the way. When it attacks that, we create yet again another tetrahedral intermediate. Now, when we make this tetrahedral intermediate, we ask ourselves, do we have a good leaving group? The answer is no. Carbon things and hydrogen things do not make good leaving groups. And so what we do is we allow for protonation. So we bring in some water. And we get the primary alcohol at the end. If you're looking at the sodium borohydride mechanism, it is remarkably similar, except sodium borohydride is not reactive enough to undergo the reaction with carboxylic acids or esters. So sodium borohydride is going to stick to reacting with aldehydes and ketones. Speaking of the different reagents that react in different situations, I feel like you should fill in this chart. I feel like we should go through and take the time to figure out which functional group each of these reagents react with. What I would like you to do is pause me, go back into your notes and fill this out and then compare answers with me when you're ready. What I'm going to do is put a check mark if a reaction happens between that functional group and the reagent, and an X if it doesn't. Let's compare. What we see is that ketones and aldehydes are going to react with each of these reagents, whereas the carboxylic acid and the ester are only going to react with lithium aluminum hydride, and the alkene is only going to be reactive with hydrogen. And of course, that hydrogen needs a catalyst like platinum, palladium, or nickel. Let's look at how to form diols. Diols are not any different than forming alcohols. The thing is you need to put 2 of them in your molecule. So if you wanted to have a diol at the end, just start with 2 ketones or 2 aldehydes or an aldehyde and 1 ketone in the same compound. And then go through and use any of the reagents that we saw that react with aldehydes and ketones to form alcohols. And that's how you're going to get a diol. We've also seen 2 other ways in a previous chapter where we created diols. One was when you started with an alkene and you used MCPBA. This gave you the anti-addition of OH, 2 OHs across the pi bond, and of course you were always watching out for enantiomers here, right? EN is your abbreviation for enantiomers. Whereas OSO4 and the co-oxidant NMO added 2 alcohols to the same face so that you got syn addition. Let's wrap up. In this video, we looked at creating alcohols through reduction. We defined reduction and oxidation. If you're in my class, we're skipping oxidation numbers and sticking with my definition. We looked at the different reducing agents that can be used to take aldehydes and ketones and turn them into alcohols. And we also saw that lithium aluminum hydride is special because it can also react with esters and carboxylic acids. And then we reminded ourselves how we can form diols. Thanks so much for your attention. This is Katoni signing out.